Okay, next up, we have Michael Hersche. Michael Hersche is a PhD student at ETH Zurich and also working at IBM. He's doing quite well as a PhD student. He already has a Nature paper on his work on vector symbolic architectures, also known as hyperdimensional computing. Take it away, Michael.
Thanks a lot for a nice introduction. So, hello everybody. I'm presenting the work with the title A Neuro-vector-symbolic Architecture for Solving Raven's Progressive Matrices. So this was a joint collaboration between IBM Research in Zurich and ETH Zurich. And in this work, we were mainly interested in solving visual abstract reasoning tasks. And one of these tasks is Raven's progressive matrices, which essentially tests the human and fluid intelligence. You might also have encountered it maybe in some of the IQ tests for job interviews, etc. So the test goes as follows. We are given a context matrix with 9 panels, which are arranged in a 3x3 grid. And the task is to find out what belongs into the empty panel at the bottom right by selecting one of the answer panels. So in this case, it would be the one at the bottom left. Those panels contain objects, and those objects have different attributes. So those attributes could be different shapes, different colors, different sizes or positions. And those attributes are governed by underlying rules. For example, in this case, we see that the color stays constant within a row, or that the number of objects at the rightmost panel equals to the sum of the first 2 panels. So 2 plus 1 equals 3. And by finding these underlying rules, we can execute them at the last row at the bottom and kind of predict what objects belong into the empty panel at the bottom right. And we can then compare our prediction against all the answer panel. And as I said already, it would be the panel at the bottom left with the 4 hexagons. So in our work, we aim to solve this problem as we as humans do, and we do it by using neurosymbolic architectures. So in neurosymbolic architectures, we first try to understand which objects are present within the individual panels. This can be done with a standard neural network, let's say CNN or a vision transformer. And then as soon as we detect the individual objects, we try to reason about the rules per row and also do the prediction what belongs into the empty panel at the bottom right. So while this combination of the neural network and the symbolic AI is very attractive, we still inherit some of the limitations of the individual parts. So in the neural network, we are facing the binding problem. So we have issues to bind certain informations, let's say the color and the shape together. And I will give some example afterwards. And in the symbolic AI side, as it has already been mentioned yesterday, we face expensive searches. And in our work, we try to address these 2 limitations by introducing a meaningful vector space that is sandwiched between the neural network and the symbolic AI. This vector space is called vector symbolic architecture, or also as high-dimensional computing. And in this vector space, we represent objects from atomic objects to composite objects with high-dimensional representations. Those representations are mostly drawn randomly at the beginning, and because they are random and high-dimensional, different objects are orthogonal with high probability. This is also known as quasi-orthogonality. So we not only have a meaningful vector space, we also have well-defined distributed vector representations, such as the unbinding, the superposition or the bundling, the binding, permutation, and inverse permutation. So by introducing this meaningful vector space, we can address both the binding problem in the neural network and the expensive searches in the symbolic AI by doing search and superposition. So now I will show you how we use this new architecture that we call Neuro-vector-symbolic architecture, or in short, NVSA, to solve those Raven's progressive matrices. So again, we are given the context panels that are arranged in a 3x3 grid. And in a first step, we pass each individual panel through the NVSA front end, which does the perception. This NVSA front end contains a trainable neural network. In our case, it's a ResNet 18 that maps the input image to a high-dimensional representation. We then compare this high-dimensional representation to all the possible elements in our VSA codebook, and that gives us some belief which objects are present in the individual panels. And then as a second step, we pass those estimations to the NVSA backend that does the reasoning. So in this case, we first detect the rule and execute it all in a high-dimensional distributed representation that is mainly governed by the VSA codebook. So let me focus first on the NVSA front end, the perception, and just shortly revisit the binding problem in neural networks. This is one version of the binding problem. It is mainly concerned finally to the superposition catastrophe. So let's say we want to recognize different objects, and those objects are governed by two different attributes, color and shape. So we can train a neural network such that we can map this input representation, this visual representation, to 4 different logits that discriminate 2 different colors and 2 different shapes. So hopefully, if we properly train this neural network, the logits corresponding to the color red and the shape square would be activated. Same should also hold for a blue triangle. So far, so good. But it gets problematic if we want to recognize 2 objects at the same time. So all of a sudden, all the logits are activated, and we end up with an assignment problem, meaning that we are not sure whether the square that we recognized has color blue or red. So this is also known as a superposition catastrophe, and we address this superposition catastrophe by introducing a distributed representation over a conceptual space. So what does it mean? So we start by defining the atomic concepts in terms of code words. So our atomic concepts are different colors, red and blue, and the different shapes, square and triangle. And for each of those concepts, we define a code word, whereby this code word is a high-dimensional representation, and that is drawn randomly at initialization and then fixed throughout the operation. In our case, those code words are of bipolar values, so they are either -1 and +1, the individual elements, and they have dimension 512. So because they are initialized randomly and they're of high dimension, they are orthogonal with high probability. So the representation of red is orthogonal to the representation of blue. So for defining higher level concepts, for example, a red square, we can use our distributed vector operations, in this case, the binding, to represent it. So the red square is just simply defined by taking the code word of red, the code word of square, and bind them together. In this case, the binding operation is simply the element-wise multiplication, also known as the Hadamard product. Same can be done for the blue triangle. And what is important here is that the binding operation is in a sense orthogonality preserving. So the representation of the red square is orthogonal to the blue triangle. And because they're orthogonal, we can safely superimpose those 2 representations that can represent both the red square and the blue triangle as a combination, while having not or like low interference between those 2 representations. So until now, I introduced how we can build up the target representation in our high-dimensional distributed space. So now we can simply train a neural network that maps those visual input data to the high-dimensional space. And this is what I will show you in the next slide. So now I will give you some more details about our actual application. which is the iRaven dataset. In the iRaven dataset, we have 5 different types, 6 different sizes, 10 colors, and 22 unique locations. So we, for representing one object, we have to bind 4 code words together. And overall, this gives us 6,600 different bound representation or combinations. So we can store this in the so-called W matrix. And this W matrix, as I said, is initialized at the beginning in the means of the code books and code words, and fixed during operation afterwards. So let's say we get again this example with the red square and the blue triangle. We map it to our high dimensional representation with a neural network, could be, for example, ResNet 18. We then compare this high dimensional representation of this image to all the elements in our code book or W matrix. And hopefully, what we end up is then a 6,600 dimensional similarity vector. And what we hope for is obviously that the similarity to the red square and the blue triangle is maximized. If it's not maximized, we can still train it with a additive cross entropy loss if you are given the ground truth labels. But this is a very supervised, like a fully supervised setting where we are provided with those ground truth labels. I will show some more weakly supervised cases towards the end of the talk. So what we found was that with this additive cross entropy loss, we can actually achieve very high recognition accuracy, which was actually not possible with other alternatives like the standard binary cross entropy loss, where we saw low classification accuracy. So maybe to just quickly take a step back, what we just proposed, or what we propose is a NVSA front end that is able to detect multiple objects with one single neural network pass. And this is not the case for other approaches, especially neurosymbolic approaches, that mostly take a two-step approach. So first, one normally takes an object detector like a mask RCNN in order to detect the individual objects and crop them, and then pass each of the cropped images through a classifier, let's say a ResNet 34. So this needs more parameters and also more compute. So now we look at the NVSA perception accuracy. So we are not yet solving Raven's puzzles, but we are still interested in recognizing the individual objects. So on the y-axis, I show the perception accuracy, and on the x-axis, I show different constellations. So this iRaven dataset has different constellations that come with different, let's say, difficulties. So for the center constellation, we have just one object per panel. For the 2x2 grid, we have up to 4 objects per panel. And then the 3x3, for example, we have up to 9 objects per panel, which obviously makes it hard to solve the overall task. So we first look at the perception accuracy of the state-of-the-art neurosymbolic approach, which is the PRI, and it achieves 85.3%. And with our NVSA front end, we actually achieve almost perfect perception accuracy. And if we can also reduce the amount of training data by a factor of 7 while still maintaining a high accuracy. So we're very data efficient. So we can then essentially map those cosine similarities I showed you in the perception to probability mass functions or some beliefs about which objects and which attributes are present in the individual panels. And those probability mass functions, or PMFs, are then fed to the NVSA backend, the reasoning. And here we rely on probabilistic abduction and execution. So what we essentially do is we first take the probability mass functions of the first 2 rows in order to compute the rule probabilities. So for each of the attributes, there is a certain set of rules, let's say constant rule, arithmetic plus, progression, distribute tree rule. And for each of those rules, we want to compute the rule probability. Afterwards, we estimate the rule by for example, taking the one with highest probability or highest confidence. And with the selected rule, we can then apply it at the bottom row in order to get a estimate distribution or probability distribution of the empty panel at the bottom right. And finally, we can then compare this distribution to all distribution of the answer panels, and we select the answer panel that is closest to our estimation in terms of divergence. So while all of those blocks are essential to solve the eventual task, what we have found was that the rule probability computation is mostly computationally expensive, and that's the one we also wanted to improve. So let me just quickly show you an example of the arithmetic plus rule on the attribute number and how a standard, let's say, symbolic approach would solve the task. So again, we are given these three panels that with the arithmetic plus on the number, we know that the number of objects at the rightmost panel is equal to the sum of the first two panels. So 1 and 2 plus 1 equals to 3. So what we are given by our perception is not kind of one-hot encoded PMFs, but some certain distribution. So we are pretty much sure that there are maybe two objects, but there is also some belief that there is just one object or even three objects. So for estimating the probability that a certain rule, the arithmetic plus, is present, we set out a truth table, and we essentially go through this truth table, and for each of the valid configuration, we multiply the probabilities together and sum them all up. And finally, we get to some conclusion that arithmetic plus is present with a probability of 0.7, for example. So this can end up with quite some expensive searches. Mostly in cases where we have large PMF spaces. So in this case, we have a PMF space which has arity 10, but there are some of them that have like up to 511 dimension. And then overall, we need to search over like more than 200 million rule realizations in some of the cases, like a distribute tree on the position and constellation. And with our NVSA backend, we can do the same computation by just doing two vector bindings and one vector comparison. And that's what I'm showing in the next slide. So we essentially implement the probabilistic abduction with arbitrary PMFs by doing search in superposition with distributed representations. So we map the individual PMFs to a high-dimensional representation. So also here, we first introduce codebooks, and we then can simply do a weighted superposition of those codebooks by taking the PMFs as weights and the codebook or code words as vectors or basis vectors. Then we can apply the rule, in this case on the first two panels. For the arithmetic plus, the rule application means simply the vector binding, and then do the similarity computation that gives us the same outcome like arithmetic plus is present with probability 0.7. Actually, this approach has some parallels to probabilistic logic programming. So here I formalized again the actual computations that we do to compute the rule probability of the arithmetic plus. So we bind the first two panels and we compare it to the third panel. And after doing some simplifications, what we come up with is that we sum over all the possible worlds where the arithmetic plus rule is true. So the sum of the first two elements is the third one, and what we sum up is the product of these three elements. And what we also have in our case with our distributed representation is some kind of noise terms, where we sum up over all the remaining worlds where the rule arithmetic plus is not true. And Here in this case, we see that we have this kind of N that describes the noise. This noise term actually diminishes with growing dimension D of our distributed representations. So now I show you the results on the NVSA reasoning in isolation. So we provide the ground truth labels of the objects to our NVSA reasoning, or also the state-of-the-art neurosymbolic approach, and we measure the reasoning accuracy and the compute time for solving 2000 Raven's progressive matrices. In this case, we focus on the most difficult constellation, which is the 3x3 grid. So when looking first at the results of the state-of-the-art neurosymbolic approach, the PRI, what we see is that even though we provide the ground truth labels, we do not achieve 100% accuracy. And that's because searching through all the possible combinations would be too much expensive for the standard neurosymbolic approach. And therefore, it limited its search space. We actually relaxed some of those limitations, and we see that we actually can improve the accuracy, which is shown with our unrestricted PRI. However, we end up with a compute time of 10.7 days. We had to run all those experiments on a local CPU because the memory of the GPUs was not sufficient to run those experiments, especially the unrestricted PRI. In contrast, with our NVSA, we can maintain a high accuracy by reducing the compute time by 240x. So this is a 2 orders of magnitude improvement. So until now, I mainly discussed the individual blocks, the NVSA front end and the NVSA backend in isolation. And now we plug them together and train them end to end. So this will be a much weaker supervision in this case. What we are provided with is the ground truth answer, so which panel is the actual answer. And we can use a reinforced loss to compute the loss. And we are also provided with ground truth rules. This is given by a data set, and we can use them to compute the auxiliary loss. We then update our ResNet 18, the weight of the ResNet 18, whereby all the other blocks are frozen. So all the VSA code books and all the rules are initialized or defined at the beginning of the training and fixed afterwards. So now we can look at the end-to-end accuracy for solving the actual iRaven data. And we see again on the y-axis the accuracy for solving the actual task, and on the x-axis the different constellations. First, we look at the state-of-the-art neurosymbolic, the PRI, which achieves an average of 71.1. This is a reproduced result. We also reproduced the performance of the state-of-the-art deep neural network, the SCL, which actually outperforms the neurosymbolic approach by achieving 84.3% accuracy on average. And with our NVSA, we outperform both the state-of-the-art PRI and the DeepNet by achieving 88.1% accuracy. We also did some investigations into the OOD generalization. So what we were mainly concerned in this task or experiment was whether we can generalize to new attribute rule combinations that have not been exposed to our model during the training. So let's say we see that we are given like certain types and rules, and we provide all the possible attribute rule combinations except of one, which in this case would be the type and progression. And during testing, we just test on this kind of combination. And what we see is that with our NVSA, we actually can maintain a very high accuracy in one of the constellations, that is the left-right, and we outperform all of the other baselines in this case. So to sum up, in this work, we present a neuro-vector-symbolic architecture that is the new state-of-the-art for solving Raven's progressive matrices. We achieve this by performing representation learning over a conceptual space on the NVSA front end. Then in the NVSA backend, we perform abductive reasoning with distributed representation operators. But we still stay transparent and we are 2 orders of magnitude faster than the symbolic backend. Our architecture can be trained end to end, and we achieve a new accuracy record on the iRaven dataset. And we see that our NVSA exhibits some degrees of OOD generalization. And our code is available, so feel free to check it out and give us feedback. And with this, I would like to thank you for your attention, and I'm happy to answer questions.
All right, thanks, Michael. Bunch of questions. Seems like the inputs are limited. If the blocks are put randomly, the inputs will be bigger and diverse. Then is your method slow in this case?
I'm not sure what is meant by the inputs are bigger. So if you're concerned about the kind of inputs we are given by our perception, we are not very limited. If it concerns about the intermediate representation in the NVSA front end, so maybe here I can show it. So here we can, like in this high dimension representation, we are working with a fixed dimension. So let's say we are working with 512 dimensional vectors. And if we can have arbitrary number of input objects, and we can represent or map them to this distributed high dimension representation, whereby this dimension stays fixed no matter how many input images you want, or like input objects you want to represent. I hope this somehow answers the question that was asked.
Maybe related to that, how does the vector space scale with increasing number of attributes and rules/constraints?
So at least let's start in the NVSA frontend for the perception. So like we have here 512 dimension, which is sufficient to support like up to 9 objects, and what we have seen. But you can easily scale it up to 1,000 or 2,000 dimensions, and then there you hardly run out of representational space, let's say. And then in the NVSA backend, so as I should maybe go to that slide. So in that case, what we essentially provide, we can compute, let's say, 200 to 200 million different rule realizations in parallel, which means that, yeah, we're working with dimension of 1,000 vectors, and we can search over 200 million rule realizations in parallel. So this is actually sufficient there.
Is the bipolar representation used across all the pipeline stages? Can you elaborate on the data formats at different stages?
Yes, that's a very, very good question. So yeah, we actually switch between the representation in between. This is a rather practical implication for us. So we are using the bipolar representation in the NVSA front end, and because it's like the binding operation is mainly very cheap to perform. And then in the NVSA backend, we use a representation which is called binary sparse block codes. So there we essentially organize our distributed vectors in different blocks, whereby each individual block has at most one element that is non-zero. And we introduced this kind of representation here to implement all these rules. So we rely on some of the more advanced VSA concepts, which is borrowed from vector functional architectures, to essentially introduce some relations between the different vectors that can be represented by these VFAs, or based on these binary sparse block codes. However, the binary sparse block codes could also be integrated in the NVSA frontend. This would be no problem at all. But it was more like a historical thing there.
Okay. Is it necessary that all the rules are pre-codified in the book? What if the sequence of objects reveals a configuration that is not embraced by the pre-coded rules?
Now that's a very interesting question again. So yes, as for now, like all the rules are hard-coded. But yeah, it would be interesting to see whether like some of the rules can be learned from data. And like one thing that for sure is present here in this case is that the rules can be applied for different attributes. So they are essentially shared between different attributes, and therefore for example, that's what we have seen also in our generalization experiments, that because the rules are shared between the different attributes, not all the attributes have to like contain all the possible rules for learning our backend, essentially, or like for learning the front end, I mean.
I'll just do two more since we have the luxury of a break next.
Yeah.
When describing the binding method, you mentioned the use of a conceptual space. Is it related to the work of garden floors? If yes, have you had any chance to investigate if the learned space complies with garden floors rules, and if the prototype obtained is somehow human interpretable, for example, for the color domain?
Yeah, honestly, I have not been exposed to that work, so I cannot answer it.
Okay.
So
Did you do any pre-processing to the input images?
No, I don't. No. Yeah, like that like yeah, we just process essentially, and this is actually quite some advantage of our approach compared to others. So other approaches, essentially, for example, crop, they already introduced this knowledge that the images can be cropped first, and then the individual images could be passed to the NVSA frontend. And things like that, we do not require this knowledge. So we can simply just process the entire panel at once.
Okay, I think Asim is rightfully going to cut us off now.
yeah, so let's have a short break, Alex. So thank you.
Okay, see you all back at 10:45 Eastern.
So in 10 minutes.
Thank you very much.